Alkynes are those hydrocarbons which contains one or more carbon-carbon triple bond. The smallest or simplest alkyne is ethyne, which contains two carbons and a triple bond. Ethyne is also known by its common name, which is acetylene. The ball and stick model of ethyne is shown here, and as we can see that in case of alkynes, the carbon atoms which are bonded with a triple bond has only two bonding sides, and in chapter number 4 we learned that molecules who have only two bonding sides around them, they have a linear geometry. So therefore the angle or the bond angle uh, at the carbon atom where triple bond is located is 180 degrees. And the geometry of alkynes at the carbon-carbon triple bond position is linear. While drawing the skeletal line structure of alkynes, a triple bond is drawn as three parallel lines, and the fourth bond on each triple bond carbon is drawn in line with the triple bond to reflect the 180-degree angle. For example, let's consider an alkyne with 8 carbons, and we know that this alkyne, because it contains 8 carbons, so its name is octyne. Just like alkenes, we need to give the location of the triple bond, and if you count, you'll find that the triple bond is present at 4th carbon, so the name is 4-octyne. The Lewis structure of octyne or 4-octyne is represented here. So when we draw the skeletal line structure, the triple bond is represented by the three parallel lines as shown here, and the fourth bond to the either side of this triple bond is shown linearly to reflect that there is 180-degree angle here. So at the triple bond position, alkyne molecule will be linear. So zigzag notation is not used at the triple bond carbon atoms. However, in remaining structure where we have single bonds such as this one, we do use the zigzag notation to represent the single bonds. The condensed structure for a triple bond is inferred from the carbon groups, or it can be drawn as three parallel lines as shown here. I prefer to show the position of the triple bond in the condensed structure. However, it can also be represented by just carbon and hydrogen atoms. In this case, we have to determine from these carbon and carbon atoms that it is an alkyne. As in case of alkanes and alkenes, the names of alkynes are also based on the number of carbon atoms in the chain, and at the end of the name we use Y-N-E or ine at the end. For example, the name of an alkyne with 4 carbon atoms will be butene. As in case of alkenes, we number the carbon-carbon chain to find the locator number of the triple bond, and we number from that side, which gives the triple bond smaller locator number. For example, in this molecule, we will number from the right hand side, because in that way we will get the smaller number for the position of carbon-carbon triple bond. And in this case, we can see the triple bond starts at number 1 position. So therefore, name of this alkyne is 1-butyne. One thing should be noted that because of the linear shape of the alkyne molecule, geometric isomers such as cis and trans are not possible. Let's practice writing IUPAC names of each of these alkynes, starting with A. So in this case, first we will number the carbon atoms, and as we can see that the triple bond is towards the left hand side, so therefore we will start our numbering from the left hand side. So it will be 1, 2, 3, 4, 5, and 6. So 6, the name for 6 is hex, and because it is an alkyne, it contains triple bond, so therefore the name ends with wine or ine. And the locator number for triple bond is 1, so therefore name of this alkyne is 1-hexyne. In example B, triple bond is present towards the right hand side, so therefore we will number from right hand side. It will be 1, 2, 3, 4, and 5. Name for 5 is pent, and because it's an alkyne, so it will end with YNE. And the position of triple bond is at number 1 carbon, so the name is 1-pentyne. For example C, the numbering is already done, and we can see that there are 7 carbons in the chain, and the triple bond is at number 3 position, so therefore the name is 3-heptyne. In 19th century, chemists isolated a number of compounds that were noted for their strong aroma, and hence they became known as aromatic hydrocarbons. The name aromatic is derived from the word aroma. Vanillin, which is shown in this picture, is one such example of aromatic hydrocarbons. It is found in vanilla beans, and this compound is responsible for the typical vanilla smell. And because it's isolated from vanilla or vanilla beans, that's why the name given to this compound is vanillin. As you can see that this compound is not exactly a hydrocarbon because it also contains oxygen atoms. However, it is still classified as a hydrocarbon compound. Studies showed that aromatic compounds have a common structural characteristic, and the characteristic is known as aromatic ring. Aromatic ring is a cyclic hydrocarbon ring present in all aromatic compounds, and in this ring we find an alternating pattern of a single bond and a double bond, or in other words, the ring is made up of alternating single double carbon bonds. The ring in case of vanillin is shown in the red. And this characteristic aromatic ring is found in all aromatic hydrocarbons. The simplest aromatic compound is benzene. Benzene has an aromatic ring with a hydrogen atom on each carbon atom of the ring, and the structure of benzene is shown here. Although the Lewis structure of benzene, which is shown here, may suggest that it has alternating single and double bonds, but studies have shown that all carbon-carbon bonds are identical. So in other words, we don't have 3 double bonds and 3 single bonds. All 6 bonds between the carbon atoms in the benzene ring are identical. And studies have also shown that these bonds are somewhere between single and double, or in other words, we can call these bonds to be bond and a half. So it turns out that the electrons in these double bonds, in these three double bonds, are shared by all 6 carbon atoms. The line structure of benzene is shown here. Although benzene may appear to have alternating double and single bonds, but the studies have shown that the actual structure of benzene is that these all bonds are identical. So I can show this with a dotted line, and this dotted line represents that all bonds are between double and single bond or bond and a half. The ball and stick model of benzene is shown here. So this is the top view and that's a side view, and you can see that benzene is a flat planar molecule, and each carbon atom is trigonal planar with 120-degree angle. Because these double bonded electrons are spread over the entire ring, as you can see with this dotted line, so these are the electrons spread over the entire ring. So these kind of electrons are known as delocalized electrons. Delocalized electrons make aromatic ring fairly stable, so therefore it is quite unreactive in many chemical reactions. Compounds containing aromatic rings other than benzene have one or more hydrogen atoms of aromatic ring replaced with a carbon chain or other non-metal atoms. For example, in the examples shown here, we can see here in this case, the hydrogen atom at this position has been replaced by oxygen and H group, and also this bulky group has replaced the hydrogen atom here. All these examples are for over-the-counter analgesic medicines such as acetaminophen, which is also known as Tylenol. This is the structure of ibuprofen, and finally on the right hand side we can see the structure of aspirin molecule, and we can see that in all of these drug molecules we do have a benzene ring, and therefore all of these molecules fall under the category of aromatic hydrocarbons. Every organic compound has a unique name that is based on a systematic rules created by IUPAC. As we know, IUPAC stands for International Union of Pure and Applied Chemistry, and that's the institution which makes all the rules for chemistry. Earlier, we applied these rules to name straight chain alkanes, alkenes, as well as alkynes. Along with that, we also learned how to name unbranched cycloalkanes and cycloalkenes. In this section, we will learn about the IUPAC rules for naming substituted hydrocarbons, or they are also known as branched hydrocarbons. In the IUPAC system, a branched chain hydrocarbon is viewed as a straight chain or a ring in which one or more hydrogens are substituted by a chain or one or more carbons, which are known as substituent. For example, we may have a straight chain hydrocarbon such as shown here. Now in this hydrocarbon, if we replace one of the hydrogen with another carbon or a chain of carbon, for example from the middle, if I replace it with another carbon such as this one, now this is a branched hydrocarbon, and the group shown in the blue, this group is known as a substituent. To name a substituted alkene or alkane, first we have to locate the parent chain. Now parent chain is the longest chain within the hydrocarbon. For example, in the example which we just showed here, our parent chain is this 3-carbon long chain. So our first part is to identify the parent chain. Remember, the parent chain is the longest continuous chain of carbons. Uh, let's take a look at the example shown on the right hand side. Let's erase this one. So in this case, you may see that we have a hydrocarbon chain. It's a Lewis structure of a hydrocarbon alkane. The linear chain is shown here, and we may think that the branch chain is the one which is shown vertically above. So if we consider this is the arrangement and the chain shown in yellow is our parent chain, then we will be incorrect, because the yellow chain contains 1, 2, 3, 4, 5, 6, 7, and 8 carbons. There is another way in which we can have a continuous chain of more carbon, and that is if we start from the top and we uh, go all the way to the right side. In this case, our chain is 9-carbon long chain. So this is the longest continuous chain. Remember, in case of alkanes, we may have bends. Bend is okay. So therefore, we can say that our parent chain is 9-carbon long chain, which makes the group shown here as our substituent. So in order to name a substituent hydrocarbon, first we have to locate or identify the longest continuous chain, which we already did, and then we need to name it. The name comes from the number of carbon atoms. In this case, we have 9 carbon atoms, so name for 9 is known, and because it's an alkane, so it's nonane. Okay, so now we know the name of our parent chain. Next part is to figure out what is the substituent and how to incorporate the name of substituent in our parent chain name. So once we identify the parent chain, and then we need to identify the substituent. So in previous example as well as the example shown here, the parent chain is 9-carbon long chain. So the name of parent chain is nonane. In previous example, we had only one substituent, but in this example, we have two substituents. So one is shown here and the other one is shown here. So next part is to give names to the substituent. The name of substituent is also based on the number of carbon atoms. So this substituent has only one carbon, and we know the name of one carbon is meth. In case of alkane, we put ane at the end. However, because it's a substituent, in substituent we put YL at the end. So the name of this substituent will be methyl. Let's look at the second substituent. In this second substituent, we have two carbons. So the name for 2-carbon is eth, and because it's a substituent, we will put YL at the end. So the name of this substituent is ethyl. So one carbon substituent will be called methyl. If we have two carbon chain as a substituent, then it will be called ethyl. If it has three carbon, then it's called propyl, and so on. Remember the common theme, the substituent name ends with YL. The other name comes from the number of carbon atoms. Okay, so now we know how to identify the parent chain and how to name the substituent. The next job is to put them together to come up with the complete name of a substituted hydrocarbon. So after identifying the parent chain and naming the parent chain and then naming the substituent group, the next task is to assign the locator number to each substituent. Locator number is the number of carbon atom at which the substituent is located. For example, in this case, our parent chain is 9 carbon long chain, and we have two substituents shown in the green boxes. One substituent contains only one carbon, this one, so therefore this substituent is called methyl. The other substituent contains two carbons. Remember, each band at the end is a carbon atom, so there is one carbon atom here and the other one here, so there are two carbons, so therefore the name of this substituent is ethyl. Our next task is to give it a locator number. Now the locator number is the number of carbon atom on the main parent chain where the substituent is connected. We can either count from the left hand side or we can count from the right hand side of the parent chain. However, the IUPAC rule states that we must count from the side which gives the smallest number to either substituent. So whichever side gives the smaller number to the first substituent, that should be the correct sequence of numbering. So what do I mean by that? So the meaning is that if we count from the left hand side, our first substituent which we encounter is at number 3 position. Let's, for the sake of argument, count from the right hand side also. So if we count from the right hand side, it will be number 1 here, number 2, number 3, and number 4. So we will encounter our first substituent at number 4 position. So because counting from the right hand side is giving us a smaller number for the substituent, which is number 3, therefore counting from the right hand side is the correct order, not from the left hand side. So let's erase the left hand side number. So now we know the number at which the substituents are located. So we know the methyl substituent is located at number 3 and ethyl substituent is located at number 6. So after identifying all of those elements, we put them together to complete the name of this substituted hydrocarbon. So in this case, first we start with the locator number of substituent, and we write the substituent which is alphabetically ahead. So for example, we have ethyl and methyl. So alphabetically E comes first, so therefore we will write ethyl first. So the name will be ethyl, and before the name of ethyl or substituent we will write the locator number. So ethyl is located at number 6, so it will be 6 hyphen ethyl. Always there will be a hyphen between a number and a letter, then another hyphen. Next substituent was methyl, and methyl was at number 3 position, so it will be 3 methyl. And then, so we are done with both the substituent. Then we write the name of the parent chain without any space or hyphen or anything. So our parent chain is 9 carbon, that's no name. This is the name for this branched alkane. If there are two substituents on the same carbon atom, the locator number is listed for both substituents. Let's, for example, let's say this is our hydrocarbon. In this case, our parent chain is this one. So our parent chain is 4 carbon long chain, and we have two substituents, and both of these substituents are located at the same carbon. So substituent this one as well as this one. Now both of these substituents contain only one carbon, so both of these substituents are this one as well as this one. So both of these are one carbon substituent, so both of them are methyl groups or methyl substituents. Now our parent chain is 4 carbon long chain, so therefore this will be butane. Next task is to number it. We can see that we have to number from the left hand side because that's how the substituent will get the smaller number. So that will be 2, 3, 4. So both of these substituents are connected at number 2. Both of them are methyl. So the name would be, when we have same substituent at same position, so we write 2 comma 2 because now we have same substituent and we have two of them, so therefore we write dimethyl, and then the parent chain, which is butane. So this would be the name of this hydrocarbon. So as we learned in the previous slide, that when the same type of substituent appears more than once, we use the prefix di, tri, or tetra. For example, in this case, our parent chain is 6 carbon long chain, and we have a substituent methyl at number 2 position, and we have a substituent methyl at number 3 position also. So therefore the name of this hydrocarbon or this alkane will be 2, 3 dimethyl. Parent chain has 6 carbons, so therefore it will be hexane. When the longest continuous chain of carbons is a ring, cyclo becomes the parent name as described previously for unbranched cycloalkanes. And an example of a branched cycloalkane is shown in this picture. In this example, we have a parent ring with 6 carbons, and we have a substituent group here, which is 1 carbon long substituent. So hence the name of this substituent is methyl. In ring compounds, if we have only one substituent, numbers are not used because it is understood that the number for that substituent is 1. So there is no need to write. So the name of this molecule is methyl cyclohexane. Notice that there is no locator number for methyl because it is understood that the locator number for this substituent is 1. If there is only one substituent on a ring, no locator number is needed. However, if 2 or more substituents are present on a ring, then the number starting with substituent that gives the lower number to all substituent is used. For example, in this case, we have a 6-membered carbon ring, and we have 2 substituents. So we can, if we start from this as number 1, we can go either clockwise direction or anti-clockwise direction. If we go clockwise direction, then the other substituent will be number 2. However, if we start with this carbon as a number 1 and we go anti-clockwise, then 2, 3, 4, 5, and 6. Notice that in green numbers, substituents are getting number 1 and number 2. However, in the other direction, it's getting 1 and 6. So remember, the smaller numbers to both substituent are the correct way of numbering. So therefore, the green number or the clockwise numbering is correct. The blue or the anti-clockwise is incorrect. Similar example is shown here. So we can start with number 1 here and we go clockwise. The other substituent get number 3 position. But if we number from anti-clockwise direction, now we are getting number 1 and number 4. So 1 and 3 is better or is correct than 1 and 4. Once we identify the locator number, we assemble them together similarly the way we did in the alkanes, branched alkanes, as described in previous slide. So first we will write the locator number. Both the substituents are methyl, so it will be 1, 2 dimethyl. Our ring is 6 carbon long ring, so 6 is hexane, so the name will be 1, 2 dimethyl. Excuse me, because it's a ring, so it is cyclohexane. That's the name of this one. In the example shown here, the ring is 5 carbon long ring, so therefore the name of this compound is 1,3-dimethyl cyclopentane. Let's practice writing the names of these branch chain hydrocarbons. So first we have to identify the longest chain. That will be our parent chain. So in this case it's easy. So our longest chain is the horizontal chain. Now we need to number it. We can number either from left hand side or right hand side, but the correct order is the one which gives the substituent located in the middle the smallest possible number. In this example, because our substituent is right in the middle, so it doesn't matter which side we count, both sides will give the same number. So we will go from the left hand side. That will be 1, 2, 3, 4, 5, 6, and 7. So parent chain is 7 carbon long chain. Substituent is 1 carbon, so this substituent is methyl, and the locator number is number 4. So the name of this will be 4-methyl heptane. Remember, this hyphen is important. Between the number and the name, there will always be a hyphen. Let's take a look at example B. Now, in this case, if we go with the horizontal chain, that will give us only 4 carbon long chain. But that is misleading. The correct, the longest chain is not 4 carbon long. There is another longest chain, and that longest chain is starting from top, going this way, and then going down. So this is the continuous longest chain, and if you count, it has 5 carbons. And the numbering will start from the top because counting from top gives the smallest number to our first substituent. So this will be number 1, number 2. See, our substituent is here, so that's getting number 2 position. So this is number 3, number 4, and number 5. We have another substituent at number 3 position. So both of these substituents are methyl. This is also methyl. So let's assemble the name now. So we have methyl at number 2 position, so it will be 2, 3 dimethyl. Parent chain is 5 carbon, so it's pent. Because it's an alkane, so it's pentane. So 2,3-dimethyl pentane. To name a substituted alkene or alkyne, First, we need to locate the longest continuous chain that contain both atoms of double or triple bond. This is extremely important, that our longest parent chain must contain the double or triple bond. For example, in the molecular structure shown here in this picture, although the longest chain is the horizontal chain, and if we count this way, the double bond is not present on the longest chain, so therefore this is incorrect. So the correct is when we select the longest chain with the double bond present within this parent chain. In doing so, it may not be the longest chain anymore, but this is the correct way. So we must find the longest chain which also contains the double or triple bond. So therefore this is correct, however this is incorrect. Then we assign the name of the parent chain based on the number of carbon atoms, and remember, in case of alkene the name ends with ene, and in case of alkyne the name ends with yne. After identifying the name of the parent chain, then we uh, give the locator number, and that we number the parent chain from the end which is closer to the double or triple bond, and this way it provides a locator number for the double or triple bond. For example, in this example shown here, we will count, or we will number from the top, because this way it will give the double bond the smallest possible number, which is number 1. Once the numbering is done, we identify the locator number for the substituent group also. In this case, our substituent is located at number 2 position, and because our substituent contains 2 carbons, so the name of this substituent is ethyl. And finally we combine the name together to find the complete name of the substituted alkene or alkyne. If applicable, we also add cis or trans prefix if they exist. In the example shown here, cis and trans are not possible because at number 1 position there are no carbon groups or carbon atom present, so therefore cis and trans does not exist. So in this case, the name of this hydrocarbon is 2-ethyl 1-butene. Let's practice the names of branched alkenes. First is we need to identify the parent chain which also contains the double bond. The parent chain is the longest chain with the double bond, so this would be the longest chain, either this way or this way. Both are correct. In both cases the number of carbon atom is exactly the same, and both will give the same answer or same name. Next is we number the carbon atoms within the chain, and we number from that side, which gives the double bond smallest locator number. In this case, we must count from the right hand side, because that's when the carbon-carbon double bond gets the smaller number. So it would be number 1, number 2, 3, 4, 5, 6, and 7. Now our substituent is located at number 3 as well as number 5. At number 5 we have 1 carbon substituent, so it's a methyl, and at number 3 it's a 2 carbon, so this is ethyl. So now let's assemble the name together. So the name will be first we write the substituent in alphabetical order. So ethyl comes first, so it's 3-ethyl 5-methyl three heptene. This 3 is the locator for the double bond, and hept is because the length of the parent chain is 7, so that's hept. And then ene means it's an alkene. So that is the complete name of this substituted alkene. Let's write the name for the other example. So in this case, our parent chain is the horizontal parent chain, and it is obvious that we have to count from the left hand side because the double bond gets a smaller number by numbering the carbon atom from left hand side. So that will be number 1, 2, 3, 4, 5, and 6. So the name of parent chain will be hex because 6 carbon atom. The substituents are located at number 2 position and number 3 position. In both cases, it's methyl group. So let's assemble the name together now. So the name will be 2, 3 because there are 2 methyl groups. So I'll say dimethyl hyphen the double bond starts at number 2, so it will be 2, and then 6 means it's hex, and then alkene means it's hexene. So 2,3-dimethyl 2-hexene. While naming substituted benzenes, the parent name will always be benzene. For example, in this example, the red ring is the benzene, so that's a parent ring, and the substituent here is methyl. No locator number is needed if there is only one substituent as shown in this example. So therefore the name of this compound should be methyl benzene. However, many of these substituted benzenes are known as their common names. For example, methyl benzene is commonly known as toluene. In this case, the substituent is ethyl and our parent ring or parent name is benzene. So the complete name will be ethyl benzene and propylbenzene in the example shown on the right. No common name exists for ethyl benzene or propylbenzene, so they are known by their proper names as shown in this picture. If there are more than one substituent present on benzene, then we do use the locator number, and the locator numbers are identified the same way we did in case of cycloalkanes. So in case of substituted benzenes with more than one substituent, we assign the locator number to give relative position on the ring, and we start by number 1 on one of the substituent. If the names of substituents are different, such as in this case ethyl and methyl, we give the smaller number to the substituent which comes first in alphabetical order. So therefore in this case we will give number 1 to ethyl substituent, and then we count either clockwise or anti-clockwise, whichever way gives the smaller number to the other substituent. So in this case, counting anti-clockwise gives the smaller number to the other substituent, which is methyl, and then we assemble the name together just as in case of other alkanes and cycloalkanes. So the name of this example here is 1-ethyl. We write ethyl first because alphabetically E comes first, and then 3-methyl, and the parent name is benzene, so that would be the complete name of this substituted benzene. Let's practice writing the names of these substituted benzenes. Remember, in substituted benzenes, the parent name will always be benzene. So in first example, we have two substituents. So this substituent is methyl because it contains only one carbon, and the substituent on the right hand side contains four carbons. So the name of this substituent is butyl. Now because alphabetically butyl comes before methyl, so we will start the numbering from this carbon to identify the locator number. So that will be number 1, number 2, and methyl group will be located at number 3 position. So let's assemble this name together. So it will start with 1 butyl hyphen 3 methyl benzene. Similarly, on the example given on the right hand side, again we have a methyl group connected to benzene and an ethyl group because it contains only two carbon. So ethyl group is here, methyl group is here. Again, alphabetically ethyl comes ahead of methyl, so therefore we will give locator number 1 here. Now if we count clockwise, so 2, 3, 4 and 5, methyl gets number 5. However, if we count anti-clockwise, so then methyl gets number 3, which is correct. So when we assemble the name together, so ethyl comes first, so it will be 1 ethyl 3 methyl benzene.